Let's move on in our discussion of Newton's laws. Today we're going to start looking at problems that have multiple objects, which is going to bring us into a discussion and use of Newton's third law. So let's start by describing our first two laws. So the first law by Newton is if there is no net force, there's no acceleration. So we've been using this. Our second law is that the sum of the forces as a vector equal mass times acceleration as a vector. And then here is our solving force problems, the steps we've been using. So it'll pretty much be the same steps that we'll use in doing multiple objects, but we'll just sort of see it as a couple different things that we'll do a little bit differently. So let's first introduce ourselves to Newton's third law. Whenever an object exerts a force on a second object, the second object exerts a force on the first that is equal in magnitude and opposite in direction. We call this the action-reaction law. And sometimes this law is misunderstood. And so let's go through and talk about this and see if we can get our heads around this a little bit better. So probably the thing that people get most confused about is this fact here, is that for Newton's third law, the force pairs we're talking about, the force pairs that are equal and opposite, always involve the same two objects. And so let's just look at a sort of real base example. So here's some person leaning against the wall. All right, and what I'm going to do is I'm going to define a way to write forces. And so here, so this is the force on the person that's caused by the wall. All right, and so that's a force that's acting on the person. Well, anytime you have a force like that, there's going to be an equal and opposite force, and we'll call this the force of the wall on the person. And so that's the gist of Newton's third law. So there's this force of the person on the wall, and it's going to equal the opposite force of the force on the wall by the person. So again, just the way that I write this out. So this one is the force on the person that's caused by the wall, and this is the force on the wall caused by the person. And what's the tricky part, again, is that these forces always involve the same two objects. And so let's look at examples. So they're always the same kind of force. And so here's a classic example. So a book sits on a table. What is the Newton's third law action-reaction force associated with the gravitational force of the Earth on this book? So go ahead and pause this and think about it, and we'll talk about it. All right, so hopefully you got B. And so let's just unpack this a little bit. So here's this book on a table, and here's the force on the book by the Earth. And so the way that it works is the answer should be the force on the Earth by the book. And so you can imagine, you know, if down here, if I had, this is the Earth, right, there'd be this force on the Earth by the book. These are equal and opposite. And so part of what's confusing about this is you know, we don't generally use the force on the Earth by the book because it doesn't really affect the Earth, right? And so it's not really something we talk about much. But there'll be some cases where it'll be really important for us to sort of differentiate this. And so one thing that people will often answer to that question we just asked is that it's the normal force. And so it's true, the normal force will often equal mg, right? But it's not always that. We've seen examples of that ourselves where the normal force is not equal to mg. And furthermore, right, what the most important part is they're not the same kind of force. And so here you're talking about a gravitational force. So it's kind of weird. We know that the Earth pulls on the book, but the book also pulls on the Earth. Now, again, it's such a small force that we don't notice it, but it's there. And so you've got to be sure that they're the same kind of force. Okay? So let's look at an example now that we can solve using this principle. And so let's look here. This is an old test question. A small and a large block, mass m and 2m, are arranged on a horizontal frictionless surface as shown below. A student pushes on the left side of the small block with a force of 5 newtons so that the entire system accelerates to the right. How will the accelerations compare of the two blocks? So go ahead and think about this one, and we'll talk about it. Okay, hopefully you got that they're equal. And this is another important concept that can help us a lot in multiple objects. And this is called acceleration constraints. So because these two objects are moving together, right, they're going to have the same velocity at any point and the same acceleration at any point. And so we can also use this to help us solve the problem. And how can we do that? Well, let's move to the next part. So we're going to kind of unpack this problem bit by bit. So one thing we can ask about this is, what is the acceleration of block M? Okay, and we'll go ahead and tell you that, we'll say that's the mass is 3 kilograms. What acceleration will block M have? So give this one a try, and we'll see what we come up with. Okay, so when I did this, I got 0.55 meters per second squared. So let's look at this. So my general rule with a problem like this is the first step is I try to think of the two objects. Because they're moving together, I have a little flexibility to think about them as sort of one big object. And so sort of like if you draw a circle around it, we sort of combine these two guys into one object. And so let's draw our free body diagram and do our usual steps. So our usual steps, let's just do our regular XY coordinate system. That's pretty easy to think about that. And over here we've got, that tells us that there's a force of 5 newtons from this side. Okay, we know that there's our good old friend, the normal force, and the mg there. So again, the mg is that force on these blocks from the earth. Now, just to be clear, right, when we do our free body diagram, we only are interested in the forces acting on the object in question. So I don't care about the force on the earth from the block. That's why we rarely mention that one. Okay, but so here we are, the 3 forces in question, and we're told this is a frictionless surface, so I really don't care about anything in the y direction. The normal force isn't really going to affect me. I'm really interested in the x direction. So let's take our x direction equation here, and again, instead of writing an x here, I'll just get rid of it since there's only one acceleration in this problem. And so actually this problem turns out to be not too bad. So it's that force of 5 newtons equals, now this would be the total mass of everything times A. And so when I solve for A, I get 5 newtons divided by that M total. And then so again, in our problem, it's 5 newtons, the mass total. So each M is 3 kilograms. So this guy's 3 kilograms, this guy's 6. And so altogether it's 9 kilograms. And so when I did this with my calculator, I got that 0.55 meters per second squared. And the thing is, because we know they have the same acceleration, this is the answer for block M. And, you know, if this question happened to ask the acceleration of block 2M, it's the same thing. And so by using that acceleration constraint, I can go through and find this out pretty nicely. Okay, so now the way these problems will generally work is like the first part will be what's the acceleration. The second part will be something a little bit more complicated. And so let's go through and try to think about how to set that up. And so when the more complicated part, you'll generally need to look at each one of the blocks separately. And so let's go ahead and start doing that. So here I got the same problem, same setup, and my question now is how many forces act on block M, the smaller block? So think about this, and we'll talk about it in a second. Okay, so I got that there's 4 objects acting on block M. And so let's unpack this one a little bit. And so what we can typically do is we'll look at both objects. So here's my block M, and here's my block 2M. And so what we'll do is, again, we won't be too interested in these, but it's nice to put them on there. And so I'll call this the force normal. I'll call this my normal force 1. And of course, there'll be over here a force normal 2. There would also be here the force mg. And here, this would be the force 2mg. Again, where that m is this sort of m we got going on there. Now let's look at this guy. So we know from the problem there's that force of 5 newtons. But this block is going to feel a force from that guy over there. And by the convention we have, this would be the force acting on M from 2M. That's what I'll call that force. And so the question asked us how many forces are acting on block M. So you look here, 1, 2, 3, there's 4 forces. Now it didn't ask us about this one, but let's go ahead and do it anyway. If you look here, there is no force over here, all right? And the thing is, it's weird. We know this 5 newtons is having an effect on this guy, but it's not actually touching that guy. Remember, our rules are that our forces have to be either gravity or something touching. And what's touching this? Well, the thing that's touching this would be what I would call the force on 2m from m. And of course, these two forces are going to be examples of one of our Newton's third law action-reaction pairs. Okay? And so the answer to that last question should have been 4, and hopefully you can see that from here. So let's move on and see, how these problems will typically evolve from here. All right, so oftentimes these kind of problems, the first part will be like find the acceleration of one of them, where it's advantageous for us to treat the two objects together. The second part will ask something like this. And so in this case, this particular question asks, what force does block 2m apply on block m? And again, in doing that, you're going to need to separate the two objects here. And so again, here's our free body diagrams. And so let's go ahead and, if you want, pause and give this a try. And again, try to figure out what force does block 2m apply on block m. Okay, so when I did this, the closest force I got was this 3.3 newtons. So let's go again and look at this. Now, what are we trying to find here? The good news is we're trying to find this force here, which is nice, is we actually have two different ways to find it, because we have two different systems here. And so this is a case where this is a a harder problem, but because of that, it's a little bit easier. So I look over, I'm going to try this one over here. I think this one is a little bit easier. And one thing that we'll need is if you remember, the acceleration of our whole system was 0.55 meters per second squared. Of course, that's the acceleration of each one of these blocks. And so that's going to be super helpful. So again, I don't really care too much about the y direction, so I'm just going to just sort of skip it for now. But for this one here, I'm going to look at the forces in the x direction just on this guy here. And again, we'll just sort of get rid of that x part there. And real careful is that here, this should be 2m. Right? And so this is where it can get sticky, is that I'm just looking at this guy. And so if I do my F equals ma, I just want to look and only use that mass there. Right? Because what I'm saying is I'm looking at the forces acting on this 2m block, and those forces in the x direction are going to equal the mass of that block times a. In this case, that is 2m. This is another case where it's really easy to kind of slip that up. And so here, if I look at that, the only force that's acting is the force on 2m from m. Now again, this particular question was asking about the force. Let's just go back. It was asking about the force does block 2m apply on block m. But because of Newton's third law, we can find either one of those two forces, and we know that they're equal and opposite. So that's a nice feature. So basically, that force will equal 2m times a. And so over here, if I take, so it's 2, and of course we know that mass was 3 kilograms, and the a was 0.55 meters per second squared. And so when I did that, I came out with the answer of 3.33 newtons. Now, you could have used the other one, and that's going to be just fine. So let's go ahead and look at how to actually do that one. And so we can also do this using this side here. Again, this is a little bit harder, but it's just nice to kind of go through and show that it works. And so again, I'll do that f of x equals, in this case, it's just the m times a. And so why is it harder? Well, now there's two forces. So it's 5 newtons minus this force m 2m. Again, it should end up having the same magnitude, and this equals m times a. And so we're actually trying to find this force. And so if I do a little bit of algebra, I'll get force of m 2m, and that should equal ma minus, I'm sorry, yeah, when I flip that around, it'll come out to be 5 newtons minus ma. And so if I plug this in, I get 5 newtons minus, again, this mass is 3 kilograms, and our acceleration was 0.55 meters per second. And if you figure this out without, if you look just sort of in rounding errors, you get the same force. So either way it works. So two things there. Either way you do it, it should work for you. And the other thing is, this gives you kind of a way to check yourself, right? So if you have a test or a quiz or something like this and you have some extra time, you can actually do it both ways and kind of double check and then be pretty sure at that point that you have the right idea. So again, for these kind of problems, again, they'll always be a little bit different, but what you can do is sort of trim together to find your acceleration, or to find, whatever sort of a global type thing like that, and then you can split them up to try to figure out these Newton's third law pairs. Okay, in this particular problem, on the test that we gave, that I gave, I had this question too, so I thought we'd try this one too. And so how does the net force on the small block, we'll call it F of S, compare to the net force on the large block, F of L? So go ahead and think about this one, and we'll talk about it in a second. Okay, and so hopefully you got that the net force on the small block is less than the net force on the large block. And this is something that goes back to Newton's second law. Okay, and so what I can do is I can say the net force S, so that's the net force on the small block, I know that that equals to the mass times the acceleration. So in our case, that's m times a. The net force on the larger block is 2m times a. And so you can just sort of see that if that's the case, then this one is going to have to be bigger. And so this kind of, for a question like this, it's really powerful, obviously, to look at this according to Newton's second law. So now the other way to do this is you can go through and find those forces. We solved for all the forces. You can actually do that and solve for the forces, but it's actually at this point easier just to say, well, I know the net force equals the mass times acceleration. So as an exercise, just if you want, you can go back and take those forces we found before and actually find the net force that way and show that it comes out to be the same as mass times acceleration. All right, we'll see you in class.